for the exam. And then we'll continue with the lab after that. So just a quick recap. Last time we talked about these different quantum numbers. And again, the quantum numbers refer to different aspects of the orbital that an electron is in, or in the case of the MS quantum number, an aspect of the electron itself. Right, so that's one distinction here. The first three quantum numbers refer to something about this three-dimensional area where the electron is going to be occupying. The fourth quantum number refers to some property of the electron itself. Right, but if we know those four quantum numbers, that's as much detail as we can get about what that electron is doing in an individual atom. And as we said, the principal quantum number tells you roughly which energy level the electron's in, and that gives you some general information about how far away from the nucleus the electron is. But the shape of the orbital that the electron is in also is important. So the L quantum number tells you about the shape. It also refers to which subshell the electron is in. So there's the S, P, D, or F. And those all have their own shapes, which we'll see what those look like here in a minute. And we'll see how the shape affects the stability of the electron when it's in that orbital as well. Remember that subshells are within principal shells, or within the principal energy levels. And within the subshell there are orbitals. So as we said, an S subshell, no matter which energy level you're talking about, an S subshell is always spherical, and it always has one orbital. And then a P subshell is really a culmination of three P orbitals. So this is what one of those looks like. Another one has a similarly shaped, or exactly the same shaped on the z-axis, and then the third p orbital lies on the y-axis. So a p subshell includes all three of those orbitals. So when you stack the orbitals within a subshell on top of one another, it approximates a roughly spherical shape. But the individual orbitals in that subshell are not necessarily spherical, right? So I wanted to point that out. And then the ML quantum number depends on the value for L. Well, just to finish this, there are 3 orbitals here, 5 here, 7 here. So the ML quantum number, that's limited by what the value for L is. We talked about that. So you want to make sure you're aware of those limitations and that you can give a set of quantum numbers that's reasonable and identify when a set of quantum numbers is unreasonable as well. So we'll look at some examples like that a little bit later today as well. All right, so more detail about S. What do the shapes of the S's look like, and where are the electrons located? So an S orbital or an S subshell is always spherical. So in this case, the term orbital can kind of be used synonymously with subshell. Normally a subshell is a larger area that has multiple orbitals within it. But in the case of the S, that entire subshell is one orbital. So whether I'm talking about the 3s subshell or the 4s or the 5s or the 1s or the 2s or whatever, that one subshell has one orbital in it. The orbital may have different areas where the electron's located, but it's still all one orbital. So, in terms of the size, the 1s is the smallest, then the 2s, then the 3s, and so on and so forth. So we would have, if we show the 4, so this slide only shows a cross-section of the 1s, the 2s, and the 3s, but if we show the 4s, it would be larger, and it would have more kind of layers of electron density or probability within it, right? So, again, the way that you want to look at these shapes is if you take the if you take the wave function that comes from the Schrodinger equation, you can get that to mathematically calculate a 3-dimensional region in space on a Cartesian plot, right? So in the x, y, z axis. So that's what this is representing. So you can imagine that this sphere is, the orbital is actually the entire sphere. It's not just a section of the sphere, right? But they're cutting it to show you what's happening on the inside of that sphere, right? So when we see the full subshell, usually we just see the 1s is small, the 2s is larger, the 3s is even larger, right? So normally we just show a spherical shape, and the boundary, or outside of that shape, the boundary for this sphere is the 90% probability, meaning that there's a 90% chance the electron's somewhere inside that sphere. So that's normally how you'll see an S. But you want to keep in mind this mental picture of what you have on this slide, because the S sphere, when you see that sphere, it's not just a sphere that has an equal probability for the electron being located anywhere in that sphere. Within that sphere, there's certain areas where the electron density or probability is higher than other areas within that sphere. So when we look at the 1s, if we take a cross-section and we have the nucleus right in the middle, where is the greatest probability within that 90% probability sphere for where the electron's located? Well, it's wherever the color is darkest. Right? And that's pretty much right next to the nucleus. This graph here also shows, as far as the distance from the nucleus is concerned, how the probability of finding the electron changes. Right? So what's the probability of finding the electron at a distance of 0 picometers from the nucleus? 0, right? So this plot starts at 0. It starts at 0, 0. So when I'm at 0 distance from the nucleus, the probability of finding the electron there is 0. The electron is not in the nucleus, right? We already knew that. As I move away from the nucleus, the probability shoots way up right away. So the highest probability location for an electron is at this distance from the nucleus. It's almost right in the nucleus. That is why, if I have an atom and I only have a couple electrons, they're going to go in the 1s first, because they're attracted to the nucleus and they're going to move into this orbital where they, on average, spend their time right next to the nucleus. Right? So that's the 1s. Pretty straightforward. Hopefully the mental picture for that is not too challenging. So if we look at the 2s now, this gets a little trickier. The 2s has a node, and the node is here. This white area here, that's my node. Right? So what is a node? Right. If you have a wave, the node is where the amplitude of the wave is equal to 0, or the value for the wave is equal to 0 in the wave function. And since these shapes for our orbitals have been calculated from wave functions, if the value for the wave function is 0 in certain locations, then the probability of finding an electron in that location is 0. Right? So there are no nodes in the 1s. The way the 1s looks is the probability of finding an electron in the nucleus is 0. Other than that, the electron could really be anywhere. We have a high probability of finding the electron at a very short distance from the nucleus, and then the probability drops off, but it never actually reaches 0 again. The probability is very, very low as we go further and further out from the nucleus, but there's no node where we know from the mathematical calculation that the probability is actually equal to 0. But in the 2s, we have a node. So since the electrons behave as waves, when we're talking about the 2s, we know a wave can have areas where its function is positive and areas where the function is 0. Those are called nodes. So these pictures of the orbitals also have nodes, some of them. And other than the 1s, every other orbital has nodes. So the node is where the wave function, or the probability of finding the electron, is 0. So if we look at the 2s, if we look at this graph that shows the distance away from the nucleus, again, the probability of finding the electron in the nucleus is 0. But then we have a node right here. So the electron can never be at exactly that distance, which is probably about 1.2 angstroms from the nucleus. It can't be at that distance. So this is a spherical node. The shape of that area where the electron can never be is a spherical shell. Okay, so there's a good probability the electron is inside of that shell, close to the nucleus, but a greater probability the electron is here at roughly this distance away from the nucleus, outside of that node. Right? So that's why we have the majority of our color outside of the node, but we do have some color inside of the node. So this behavior of electrons means that they're not particles. We're not entirely able to describe their behavior by just treating them as particles, because it's impossible for a particle to be in this area close to the nucleus and then later in the area outside the nucleus without ever going in between. But it can't go in between because there's a node. Not even for an instant can the electron be on the node. It's impossible for the electron to be at that distance where there's a node. So this means that the electrons are behaving more like waves when they're in these orbitals. So the wave function tells us that, and it matches with experiments that you can do, it tells us that the further we go out from the nucleus, every time I go to the next energy level, there's one additional node. That's the way that it ends up being calculated. So in the 0 nodes, in the 1s, 1 node, in the 2s, and 2 nodes in the 3s. And we see on average the distance from the nucleus, where the highest probability of finding the electron is greater and greater as we get to higher energy levels, right? Which we already knew. But again, even in the 3s, there's still some probability that the electron is at this distance. Right? There's an area inside here, inside that first node, where the electron could be located, or at least it behaves as if it's spending some time in there, at the same time that it's spending time in this area between the two nodes, and at the same time it's spending time outside the two nodes. So you want to think of the electron as a wave, and since the wave can have positive values in multiple locations at once, the electron is behaving as if it's in multiple locations at once, based on the shapes of these orbitals and wherever the darkest areas are being the highest probability areas for the electron. And the average distance the electron is from the nucleus determines its potential energy. Right? If the electron's close to the nucleus, it has a low potential energy because it's held in a position it's not likely to move away from because that attraction is holding it in. If it's farther away from the nucleus on average, it has a higher potential energy. It's more likely to either move closer if there's space or get pulled away by some other attraction that it might have to the nucleus of another atom that might be nearby. Any questions about that? Okay, so those are all S. So those are the shapes. Hopefully you can imagine what the 4S and 5S will look like by just continuing this trend into larger and larger orbitals. But again, the S subshells all have a quantum number equal to 0, and they can all hold 2 electrons. How many orbitals does this figure represent? That figure represents 1 orbital. Okay, so I know that sometimes when you see multiple areas, because there's a purple area here and a purple area here, when you see multiple areas, those areas don't necessarily represent multiple orbitals. Okay? So this is the 2s. This is 1 orbital. That orbital can hold a maximum of 2 electrons. And when those electrons are in that orbital, they behave as if they're all over the area with the darkest color at once. Okay, so you can have 1 orbital that has multiple regions in it, but the electron is everywhere in that orbital at once. So that is the S. So this is what the P looks like. Where's the node in this P orbital? Try that again. Where's the node in that P orbital? So, right, so we can't have anything, so this is where my nucleus is, at the origin there. So just like in the S, in any of the orbitals, the electron is not in the nucleus. The probability that it's in the nucleus is 0. If you recall, just a minute ago, the S orbital had spherically shaped nodes, right? The nodes were a sphere at a specific distance away from the nucleus where the electron could not be. What's the shape of the node in a p orbital? In a p orbital, the node is a plane. So what these p orbitals have in common is there's some chance of electron density here and some here, but there's a plane here that separates those two lobes or areas of that one orbital where the electron can never be on that plane. Right? So, for example, this is the PZ, or so within the 2p subshell, there are 3 orbitals: 2px, 2py, and 2pz. And the x, y, and z refer to which axes of the coordinate system those lobes lie on. So the 2pz is here. There's a good probability that the electron is somewhere close to the z-axis. So in the 2pz, the electron can never be on the x, y plane. That is the node. It's right. The node is the xy plane. In the 2px, the electron density lies on, somewhere in these regions on the x-axis. So in the 2px, which plane is the node? The yz plane, right? Right. So each of the 3 orbitals lie on different axes. And so, again, each of these orbitals can hold 2 electrons, right? So this shape is not 2 orbitals. And sometimes students get this mixed up. This is not an orbital, and this is not a second orbital. Right? The situation that we have here is the wave function created this shape where this entire thing is 1 orbital. And it has 2 areas where the electron can be. The electron can never be in between those areas. It has behavior as if it's above and below that node plane at the same time. Right? So again, any one orbital can hold a maximum of 2 electrons. So I could put 2 electrons in that area. How many total electrons fit in the entire 2p subshell? 6, right? 2, possibly a maximum of 2 in each orbital, right? And again, if I were to stack these on top of one another, it would kind of approximate. So I've got 1 orbital here, I've got another orbital here, and then my 3rd orbital would be on the other axis. So that would be a total of 3 orbitals. And when I stack them, which is the way it actually looks, it approximates a spherical shape, right? So this spherical shape, though, has 3 orbitals and can hold up to 6 electrons. This spherical shape here has 1 orbital and can hold up to 2 electrons. Right? So you want to make sure you distinguish the number of orbitals in each subshell. Any questions about P? Also, just to point out, when L equals 1, that's a P subshell. And we just said there's 1, 2, 3 orbitals in that subshell. Each of those 3 orbitals has its own individual ML quantum number. Right? So the L quantum number refers to the entire subshell. The ML quantum number refers to the individual orbitals that are within that subshell. What's the... All right, that's not working. I'll write it over here. What's the ML quantum number for an S subshell? 0. any S subshell, L is 0. That's what S is. So if L is 0, ML must also be 0. It's the only possible value, right? Because there's only one orbital in an S subshell. So here are what my D's look like. So as we said, when L equals 2, that's your D subshell. And so when I have L equals 2, the possible ML quantum numbers range from -2 to +2, and there are 5 possible values, each of those representing a different one of the 5 possible orbitals. So there are 5 orbitals. So 4 of these 5 look similar, and one of the 5 is different. So let's talk about the 4 similar ones first. How many nodes are there in this orbital here? 2. There are 2 planar nodes. So probably it's harder for me to draw the planar nodes in that one since one of them is coming out at you. So it would probably be easier for me to draw them in this one. Well, I have one planar node here on this axis, right? That splits these lobes in half. So for this one, the planar nodes are on the XY axis. And where is the other? Get rid of this. Where is the other planar node here? Yeah, it's the XZ axis. Other than those 2 axes, the electron could technically be anywhere except in the nucleus. Right, so the nodes and the nucleus are the only areas where there's 0 probability of finding the electron. And this shape here, this barrier here, represents the 90% probability that's somewhere within that barrier. Any questions about that? So having 2 nodes on 2 different planes splits this thing into 4 regions. That's why we get the 4-leaf clover type shape, or the, the 4-lobed shape of the d orbital. And this one is a weird shape. It has probability of finding an electron here and here, above and below the XY axis, and then there's also a probability in this donut region of finding the electron. So that one has kind of an unusual kind of area within that donut that is a node. Other than that, there's not too much else you need to know about that particular orbital.